if you're going to work with a kid with autism and you want to teach her to select the green triangle, you don't show her green triangles and say this is a green triangle. You first teach green, you then teach triangle, you then put it together. Teach compound discriminations as independent discrimination events, and then you combine them. That's the way you teach with efficiency. So let's do that. So let's do the easy ones. Always start with easy ones. Everybody then is, very, very confident. Then you get more and more complicated. So a set of data, single phase, level. Level is simply the average of the phases. The difference is we typically think of it not as a point but as a line. So I want you to start thinking from now on. In single case data, I want you to be thinking about time and serial dependency. As statisticians, autocorrelated serial dependency is a bugaboo. For single case data, it is a blessing. It is what we depend on. We actually like that. And that's always hard from a statistical perspective. So part of what I want you to be thinking is change over time. So there's level, and we look at that, and then we start getting into the normal things where how is the level affected by trend? Well, once you look at trend, the level suddenly doesn't become as good an indicator, right? So we looked at these, and we'd say, well, when you look at that, the red line looks like a really good descriptor. If you had to combine all of those, we had 2, 4, 6 data points at about the red line. And here we have 2, 4, 6, 8, 9 data points at about the red line. Here, we've got 2, 4, 6, 8 data, but the red line, it's like saying, the clock that's stuck is correct 2 times a day. It's like, yeah, that's the middle, but come on, who cares, right? So trend creates a problem. But you knew that already, and you can build that into your algorithm. And in fact, do we do that as you could say? Well, we could talk about the top part as being, the last 5 data points are about this. But come on, now you're sort of stipulating on level. I want you to give up level, all right? I want you to free yourself, all right? Exercise yourself from the constraints of levelness. All right, level also becomes less exciting when you've got high variability. So yes, level is important. We like the level. But when you're talking about level across serial dependent data across time, you interpret it differently. It's not the middle of a set of independent scores. It's the middle of a set of dependent scores. Now, David has done some brilliant work showing that serial dependency in many cases is over-credited with evilness. But I'm less concerned about that than I'm about the concept of the extent to which you're looking at data across time. So here's what I want you to think of. Level is important, but changes in trend, changes in variability, alter how much confidence and weight we give to level. Fair enough. All right, well that's cute. So let's talk about trend. Trend is basically the slope of the best fit straight line. You can do it also, as David showed us, you can make quadratic equations, you can make it much more curvilinear. But, is it going down? Is it going up? What's the rate? What's the draw that you're looking at? And you can get describing the slope. Now you say it's got a level of this and a slope of that. Very nice. It's better if you don't have data that are in a sine wave, because then you've got, right, that's going to be even more tricky, although we don't see a lot of that. We see some, but not a lot of human behavior looks that way. So, level, trend, or slope. You with me? All right, this is the easy stuff. This is meant to be easy. So all that I'm doing is saying, I want you to pay attention. And you can either do this as a quadratic, or you can say, look, this basically has 2 patterns within a phase. We've got a downward pattern, and then the last 2, 4, 6 data points even out. Now, one of the things that we're typically looking for, how many data points do you need? You need a minimum of how many? 5, yes. But where's the 5 come from? The 5 comes from the statisticians who say 5 is better than 4, is better than 3, is less than 10. You know, I mean, it's like the reason is we begin in the data that we see to be able to trust a pattern when we see 5. If we see 2 or 3 data points, we just don't have enough that we can believe the pattern. Because, now look, here's the reason. I want 2 patterns. I want the observed and the predicted. The observed is cheap. The predicted is golden. The more data you have and the more consistent those data are, the stronger you're going to be confident you can predict the next 3 data points, right? All right, so if I look at the best fit straight line, where are you going to put the next 3 data points in this graph? You're going to put them right in here, right? That's what I want you to start getting good at doing. All right, variability. Now, variability can be calculated in lots of different ways. People like to talk about the range, right? So the top and the bottom, that is one way of looking at variability. All right, don't do that. In single case methods, I want you to calculate the best fit straight line and calculate variability about the best fit. If you want to do a curved line, that's cute, that's fine. But do it around. Now that's going to be a much more useful metric for looking at, and you can do it in terms of standard deviations, you can do it in confidence intervals. Here's the point. I want you to tell me what's the trajectory and what's your confidence about that trajectory. What's the trajectory and what's the confidence? So when you look at variability, variability is going to also affect those confidence intervals. And the thing that you now got is, look at what we've done. So far, we're only talking about data within one phase, level, trend, and variability. Now, as soon as you start talking about comparing 2 phases, then we want to say, how does level change? How does trend change? How does variability change? And a way to do that is to look at overlap. Now, overlap, in most cases, you take the range of the data in phase 1 and you extend that and say what proportion of the data are in phase 2. And you saw the 8 different variations of how to look at that. There are all sorts, you can use medians, you can use all sorts of different variations of doing that. But in truth, there are certainly examples where we say here the level changes, the trend is about flat in both cases. Because we don't have a change in trend, we trust the change in level. So we get a change here, both in level and in variability. Oh, you knew that. Okay. And it's very different. You know, the thing about overlap is a way of pretending that we're looking at a change from what's predicted on the assumption that the trend is flat. When the trend is flat, looking at overlap is neat, really neat. When you've got trend in the data, looking at overlap is much less interesting. So the deal is, all right, Peter, you're building this. You've got to build in little weights, right? And so the weight that you give to change in overlap level is really high if there's no trend. It's really low if there is trend. So here we go. Very little overlap, right? So the data in phase 2 the mean is different, right? No change in trend, no change in variability, but the problem is these data are exactly predicted, not exactly, but pretty much predicted from what we see. This is not a change. I want to say, remember, what's the question? The question is not, are these different? Come on, that's not it. No. The question is, are these data different than we would have predicted? Are they a pattern that's different than we would have predicted? Tell me the pattern. The pattern is a whopping decreasing trend with minimal variability, going down, and we're getting a little asymptotic as we get to 0, but come on. Make sense? Don't get caught up with the arithmetic. I want you to be clear when you ask the question. It actually, now you can do that, but it gets a little more complicated, right? Okay, so the other thing, and David really, he said exactly this. This is just a picture of it. When you look at non-overlap, we're wanting to talk about non-overlap as an effect size measure. So more non-overlap would be a higher effect size than less. So here's two sets of data. I would argue that this effect is greater than this effect, assuming that the ordinates are the same. But they both have exactly the same, so you've got a ceiling effect to your effect size measure. All right. Basically, that's just a very simplistic example of why we're very cautious about overlap measures. Now, so we've got this issue of serial dependency. We've got these questions that we're asking. A lot of the pieces don't quite fit, and I want you to come back. The rule that I'm recommending: always start with design. From design, always go to visual analysis. From visual analysis, add statistical analysis. You're going to choose what statistics to use based on the way in which your data in the study are laid out. The thing that I want you to take away: simple parametric models don't work because you violate the assumptions. Simple non-overlap doesn't work because it doesn't fit the real question that we're looking for, except in situations where all of the phases have basically flat trends. All right, so let's look at some of the other pieces. So immediacy of effect. I'm going to argue that if I'm working with a group of kids who have for a long time really not had very much attention, and I come over and I say, I, who am somebody to be loved, really value what you are doing, and here is the specific behavior that you are doing, and I'm going to keep watching. And I do that a certain number of times, I'm going to get not just an increase, I'm going to get a whopping increase. Really fast, really big. The speed of the increase is in part linked to my logic model. My logic model claims if I make that independent variable change, I'll not only get an effect, I'll get it quickly. All right, well, what's quickly? All right, show me you can do it within 3 sessions. All right, show me you can get the effect. So, in this case, we're going to look at the last 3 data points from phase 1, the first 3 data points from phase 2. You can make the case to have it be 4 and 4 or something of that nature, depending on if you're counting the dependent variable that you're measuring. But you get the basic idea. Now, if I look at that, is there a change in the level of the last 3 data points and the first 3 data points? No. Is there a change in trend? Yes. Is there a change in variability? No. So, I'm a little worried. I'm worried about trend with 3 data points. So, I'm going to give that less clout. But look at the difference. How about there? 3 data points. Notice there's 100% overlap with these data and those. And yet I'm going to argue that those 3 data points document a whopping change. That's not what I would have predicted. See the difference? Immediacy of effect. Consistency across similar phases. This is the one that is a little less well defined. So you take baseline to baseline, intervention to intervention. Do these data look more like those data? Do these data look more like those data? And this is, come on, those of you who are in group design heaven, this like says, do these two sets of data look like they come from one distribution and these come from a different distribution? I mean, you're basically asking that kind of a question. And the thing that you've got to put into effect is this is a point where you're producing change from here to here. So you're not expecting it to be exactly like the baseline. You're expecting it to have some of the stimulus properties. And you know how to do that. Okay, so the big thing that I'm trying to emphasize, there are 6 variables that I want you to look at. All right, you got them? Should be able to have them by now. Level, trend, variability, overlap, immediacy, effect, and consistency in similar phases. And if you can come up with an acronym or a theme song that combines those, all right, you let me know. And we will put it on the